Here I show you some examples. Cell phase modulation induced by a chirpless Gaussian pulse. Okay, so I assume my input pulse is a Gaussian pulse. This is the corresponding intensity or power profile, standard Gaussian function. What is the meaning of chirpless? What is chirpless Gaussian pulse? Chirpless means there is no temporal phase function. So the intensity function is a Gaussian, and there is constant phase in the time domain. Okay? If your intensity profile is standard Gaussian, but your phase is not constant, maybe it's a nonlinear function, then the simulation results will be different. So I have to emphasize all these results come from the assumption that no nonlinear phase function. The phase is constant, okay? But it's not plot here. I only plot the Gaussian intensity, okay? And without any simulation, you have already known what is the spectrum of your temporal Gaussian function. It's still Gaussian, right? Because Fourier transform of a Gaussian is still a Gaussian. So I use the gray shaded curve area to represent the input power spectrum. So big A absolute square, the input power spectrum. So the blue one is the input intensity. The gray one is input power spectrum, okay, without any SPM. What happens if there is some SPM? I assume two examples. First, delta phi max is only half pi. So that means SPM exists, but it's not important. The maxima phase shift is below pi, it's only 0.5 pi. And the simulation tells us the corresponding power spectrum is the red curve, okay? Here, I preserve the area. So you can see the red curve is shorter, right? But a little bit broader than the gray one. The area is conserved, it's the same, okay? But roughly speaking, the spectrum is still a Gaussian, not far away from Gaussian. And the bandwidth does not change much. Actually, if you observe FWHM, there is no big difference. You can tell the difference simply because I normalize the two curves to the same area. So you can see something here. You can tell the difference from the spectral wings. If you observe the FWHM, almost the same. So this example shows if your SPM is nominal, it's not strong, your spectrum could be similar to the input. A second example is very different. If the maxima frequency shift now is 5 pi, it's big enough, the output spectrum is represented by the blue dashed curve. You can see now, not only the spectral is broadened, you can see significant spectral broadening, right? But also, the shape is totally different, right? There is no sign about the original Gaussian shape. This is a very ugly shape, right? Okay. So maybe you can keep these curves in your mind. What would be the impact of SPM? Not just spectral broadening, but maybe, usually, totally distortion of your spectral shape, okay? And interestingly, people observe if delta phi max is m times pi, m is some real number, okay? The output spectrum has m peaks. Just observe the second example. When delta phi max is 5 pi, so m equals 5, how many peaks from the blue curve in this example? Okay, 1, 2, 3, 4, 5. Right? You have 5 peaks, and you can try by yourself. If you increase m to 7 or 10, will you see 7 or 10 peaks from your simulation? I think it's true. Okay, roughly true. Okay, so this is a very interesting observation. Okay, but I would like to raise one bonus question. Okay, why are these spectral peaks? Okay, here I only give you the simulated results. Supposedly they are true. Okay, no error. But could you justify why cell phase modulation effect will create these multiple peaks instead of a broader and a broader Gaussian function? Input is Gaussian, right? Why not just the spectral shape is still Gaussian but broader and broader? Here we see not just broadening but also significant shape distortion. And the signature of the shape is there are many peaks. Why there are so many peaks?听得懂我的问题吗？我现在不是问你为什么会展宽，这个我已经说明过了。我现在只是问你，除了展宽之外，为什么这个形状还会这么奇怪？有好多个 peak 跑出来，不只有 peak， 当然也会有 valley， 有 peak 有 valley。Why？ It's a bonus question. Please.
是因为它其实展宽之后，它其实产生很多种频率，但是有部分的频率是被破坏掉，就只有剩下特定频率留下来。
以结果论没错哈。For example, here， 你可以说频率被破坏，所以这个 frequency， 这个横轴是 frequency， 这个 frequency 的 power 没有出来，几乎是0。那有些 frequency 像这个频率被power 被 enhance， 有些 power 被 decrease。对啊，但是原因是什么？为什么有的会被 enhance， 有的会被减弱？驻波 or in physics， 你什么时候会看到有升有降，有升有降？什么物理机制会造成 interference？ Good. But what interference? Could you describe it in more detail? 波形什么波形？原来的波形非常漂亮哎。只是一个高悬，为什么有这么严重的干涉？ Okay, I can offer you one hint. Let's go back to previous page. Okay, here. So look at the left figure. For example, 这是 frequency axis. As I mentioned, some frequency maybe here destructive interference, here maybe constructive interference, right? 就是你不断的改变观察的 frequency， 有时候建设性，有时候破坏性。那怎么从左边的图来 justify 这件事 ？Remember, if you want to observe interference, the criterion is there must be at least two players, right? If you only have one player, there is no interference. 你只有一个玩不起干涉，你至少要2个以上才会有干涉，对不对？那似乎是告诉我们，某个观察频率不会只来自一个 source， 它有来自1个以上的 source， 它就有机会干涉。Yeah, you can try. How about using the left figure to justify?
because the same delta omega appears at one near the center and at the width.
Good. So, for example, if I observe one delta omega, okay, sorry, delta omega, you have to draw a horizontal line, right?
One at the center and one at the
And it passes through 2 points. So that means a single delta omega comes from 2 instants, right? And these 2 instants, okay, maybe here it has a phase here, another instant a phase here. And if the phase difference is 0, 2 pi, 4 pi, and so forth, what do you have? Constructive interference. Then that delta omega may be corresponding to here is enhanced. But if you observe a different level, okay, a different delta omega, you see different combinations of 2 instants. And the corresponding phase difference, okay, always phase difference matters, okay, is pi, 3 pi, 5 pi, and so forth. What do you have? Destructive interference. So the frequency components is almost 0. Okay, so even you have originally a very smooth Gaussian curve. The green curve is nothing special, but because of the interference nature, your output spectrum could be of very strange shape. You have multiple peaks, multiple valleys because of the interference. 我用中文说明一次，好，我们看一下下一页。我在观察不同的频率，比如说观察在这里，它距离我的中心频率可能代表某一个 delta omega， 对不对？好，那这时候为什么会 constructive？ 那另外一个 delta omega 为什么会 destructive？ 就来自那个时间组合。某一个 delta omega 我就切一个水平线，你会找到2个焦点，对不对？就代表这个时间也会贡献到那个 delta omega， 这个时间也会贡献到一样的 delta omega， 所以最后那一个 frequency component 是来自这2个时间成分的能量贡献，能量都从这里来。好，能量这里来，但是它有相位的问题，所以继续往上看，它有它的 phase， 它也有它的 phase， 这2个的 phase difference depends if they are the difference is modulo integral multiple of 2 pi， 那这2个能量贡献会建设性干涉，最后就造成 frequency component enhance。但是其他的组合你可能会看到破坏性干涉，或者 somewhere in between。OK， 所以你最后看到的 output power spectrum 会有很多的 peak 跟 valley，and it's almost universal， 你很难躲掉这个情况哈，你看，我们即使 input intensity is a very smooth Gaussian curve, you still see this strong interference effect. Okay. Now a further question is there any pulse shape? Forget about the Gaussian. If you change the input pulse shape, you will change the blue curve, right? You will change the green curve. Is there any input pulse shape that will bypass the interference? No interference. 有没有可能？有没有什么样的 pulse shape 给你的 green curve 就不再有一切过去有2个焦点？比如说你切过去只有1个焦点，这件事就没了。Excuse me？
就只有在最高点和最低点的时候这样子。
你说绿色的 curve， 只有在最高最低只切到1点，对对对，所以这个 shape 大概就很难躲掉这个干涉的特质。那我就说，我又不一定要Gaussian input pulse， 我可以想象各种的 pulse shape， 有没有哪一种 pulse shape 它对应出来的 green curve 就不会像这样子？大部分的时候都看到2个焦点，有没有？
square pulse 有这种东西。
有啊，有 square pulse。If you have a square pulse， what is the corresponding blue curve? A square but upside down, right? What is your green curve? A very strange function, right? For square function, in the middle, the slope is constant, so derivative is 0. Only at the two edges you have infinity, minus infinity and a positive infinity. So that is a very strange delta omega. Okay, then you can expect the corresponding SPM output spectrum will be of different shape from what we just observed. Okay. Then you can try, how about the triangular pulse? Okay. But maybe you can conclude, except for a few very strange examples like square pulse, most of the pulse shapes suffer from the same situation. 都会有这个事情. So you will see interference in the frequency domain usually. Okay. Very good. Let's move on. Here I also have to remind you, these figures are very useful, okay? But be careful, the output spectral shape highly depends on the shape and the chirp of the input pulse. These are simply examples based on the input pulse is chirpless Gaussian. If you have, like we just discussed, square pulse, triangular pulse, different shapes, the output spectral shape would be different. Besides, even the shape is still Gaussian if you purposely introduce input chirp, okay? Your phase function is not constant function, it's quadratic function or cubic function. It will distort your output spectral shape as well. But unfortunately, you cannot have analytic solution. You have to rely on numerical simulation to observe. So these are useful but not universal. Okay, so if you walk in the lab and from your optical spectrum analyzer, you see something different from this, don't be surprised. It's not because of your instruments is broken. It's possible. Okay, your output spectral shape naturally depends on your input pulse shape and input pulse chirp. Okay, then before we conclude this subsection, let's talk about the Kerr lensing effect. Okay, cell phase modulation effect comes from Kerr effect, right? But it's observed in the time or frequency domain. How about the spatial domain, 空间上? Kerr effect has some impact in the spatial domain as well. Okay, but let's start with a very simple example: collimated CW Gaussian beam. Okay, what is the meaning of collimated? In Mandarin, it means 准值. So if you use this word, maybe you can neglect the divergence of your beam with propagation. If it is collimated, you can roughly assume the beam will not change its cross-sectional area as it propagates. In practice, this is not true, right? Any optical beam has some diffraction effect. So gradually it will diverge. But if within a certain distance, maybe we can assume it's almost collimated, no beam divergence. Okay. What is CW? Single frequency. So that means we don't consider optical pulse in the beginning. Okay. Then the spatial intensity profile can be characterized by this simple function. Your intensity I is a function of R. R is the radius in cylindrical coordinates. Okay? So you have I0, it's a constant. The on-axis intensity. On-axis means R equals 0， 就是 z 轴。OK， 所以在已经准值的情况下 ，z 轴的 intensity 不会随着 z 改变 ，it's a constant because of the assumption collimation. Okay, but the beam's the intensity does change with radius r. Okay, so there is a Gaussian profile e to the minus 2 times r over w parentheses square. What is w? Beam radius. Okay, and because we have assumed it's a collimated beam, so w here is a constant. It does not change with z. In real Gaussian beam, both I0 and w will change with z, right? But here, because of our assumption, it's very simple. I0 is a constant, w is a constant. Your light intensity only decays as a function of r according to the Gaussian profile. Okay. Then what happens? This is very simple, right? But what happens if there is optical Kerr effect? As we mentioned, Kerr effect is characterized by a single parameter, N2, and it's always positive. N2 means the larger the light intensity, the larger the index of refraction. N2 times I is the index difference, right? So if you consider I of r together with positive N2, what happens? Imagine initially you have a homogeneous medium, like a piece of glass. If there is no optical beam, the index of refraction is a constant, independent of position. It's just a homogeneous medium. But if you shine the glass with this optical beam, the light intensity will change the index because of the Kerr effect, right? And the change is not homogeneous. The change follows the same function of r. So it's a Gaussian profile. Your index distribution now, because of the optical Kerr effect and I of r, is a Gaussian profile. And with cylindrical symmetry, right? So you can create a waveguide. What is waveguide? You have higher index at the middle, lower index in the surrounding area. That is waveguide, right? And because positive N2 and I of r, don't you create a waveguide because of the Kerr effect? Correct? Then the next question is, what is the impact of the waveguide? It's easy. By the term waveguide, you know the function of a waveguide is to confine your electromagnetic field within a small area, right? So the stronger the index, the stronger the guiding effect. Okay? And the guiding effect means the capability to reduce your beam size. 你有一个波导，先天上它就是会把电磁场局限在一个小范围。这个波导如果越强，它是不是局限的能力越强？它就会把你的电磁场分布压缩的越小。So intuitively, you will see a smaller W beam radius when the light intensity is stronger, right? So that is what I intend to show you, just like this figure. Without the material, your input is a collimated CW beam, so the beam radius does not change with propagation. And in the middle, you have a Kerr medium. And because of the optical beam together with N2, the optical Kerr effect, now you have a natural waveguide. So I use the darker tone at the middle to represent higher index regions. And the lighter tone in the surrounding area, indicating the lower index region. So there is a waveguide here. Okay? And what happens? When your input beam interact with the waveguide, the beam radius will be reduced. So your beam becomes narrower. And this effect will continue. That means when your beam cross-section area is smaller, your light intensity will be enhanced because there is no loss of energy. So if your light intensity is stronger, then it will further enhance the waveguide effect, right? So you will see a stronger and stronger waveguide, so your beam size will be smaller and smaller until at the exit of your material, you will see a smaller beam but with higher peak intensity. And this is something like a lens, right? Focusing lens. That's why it's named the Kerr lensing effect. Okay, without using any real lens, just shine your laser beam into a piece of material, the Kerr lensing effect will automatically focus your beam. Okay.